yeah, we started like just tackling problems one by one once we started the company. The hand was like would break like every few minutes or so when we started the company, and within like 18 months with just the $500,000 from angel investors, we got it to a point where you could like throw it across the room, and you know it'd still be okay. The biomechanical hand would still be fine. So sort of inherent to the design, it's very robust to perturbations from the environment, and the hand was also durable enough for us to bring here to the Bay Area to demo you guys and get sort of seed financing through Initialized. Yeah.
Hey Dhanush, thanks a lot for joining.
Thanks for inviting me.
So what does Clone do?
Clone is making musculoskeletal super intelligent androids. So these are the synthetic humans straight out of sci-fi. So the founding insight for this company is that if you have an artificial muscle technology that approaches human skeletal muscle in performance, then the subsequent musculoskeletal android with these muscles attached at the anatomically accurate points on a natural human skeleton will result in truly human level androids by strength, speed, range of motion, dexterity, and all the aspects of a human's actuation system to, or basically you have everything you need to reach human parity in actuation.
And with the assumption that that's much harder if you're just doing it with basic robotics.
Yeah, we don't have to engineer robots in the traditional sense of figuring out the exact type of shoulder actuator to, get close to mimicking the natural movement of your multi-jointed shoulder, or a specific hip joint or a specific knee joint with just the right force, and inventing sort of custom actuators for every one of those joints. Instead, we just have to focus on this artificial muscle fiber, getting to human skeletal muscle level contraction displacement, contraction force, contraction speed, with consideration to some other characteristics of the muscle as well, like efficiency, power density, response time, and so on. So the focus on the artificial muscle fiber is what allows us to build under this design philosophy of just actuating a natural skeleton to make these very radically different robots that are much cheaper to manufacture while also achieving these very high performance characteristics.
Awesome. All right. And so like building robots in a radically different way from the ground up is a fairly ambitious project. How did you come, what is your background and how did you come to this?
Sure. So my co-founder and I, neither of us are actually traditionally trained roboticists, but we both just badly want truly human level androids in our lives, something that we can say can do anything that a human could do. For me, I had exposure to various classes of artificial muscles when I was in high school. Dielectric elastomers, liquid crystal elastomers, helically coiled polymers, different types of yarns and so on. And all of these muscle fibers, when actually put head to head with skeletal muscle, would fall short on some dimension. For example, at the time, liquid crystal elastomers had a very slow response time for very thick fibrous elastomers, fibrous LCs, or rubbery LCs. Either way, it was just it was getting maybe sufficient contraction force, contraction ratio, but it would fall short on response time. Or if it had sufficient response time, it would sort of dip in the contraction displacement and wouldn't achieve the same level of range of motion that our floating muscles today can. My co-founder Łukasz had been doing research on fluidic muscle specifically for several years. This is the McKibben type muscle that was invented in the 1950s by Joseph McKibben. And with this kind of fiber, you can achieve by simply upping the pressure in the system, the flow in the system, your contraction ratio, contraction speed, contraction force, and sort of he spent years iterating on this until he was able to put out some quality demos of anthropomorphic hands on YouTube. And I caught wind of one of these videos and became fairly obsessed with the idea that I could start working on these right away, maybe without even much financing. And I decided to move to Poland, and I decided to first visit Łukasz in Poland, and we met in person and hit it off super fast. And we'd already been talking on Facebook for a year, it's pen pals, about all this stuff and how we might compactify the hydraulic power unit and all these other sort of adjacent problems to making a robot specifically work with fluidic muscles. But when I went out to Poland, we met. We're pretty certain that we wanted to do this thing together, that we could find a path out of some of these kind of problems that were dead ends for maybe decades since the McKibben muscle was actually invented, and it was sort of very exciting time to figure all that out. And within a couple of weeks, I raised $500,000 in financing from some angel investors, and that was enough to get us started for the first 18 months of the company.
And so when he was doing this with the end goal of an entire Android in mind.
Yeah, exactly. Yeah.
Okay. And so he got far enough to like get the hand working, and then you recognize that someone had kind of come to the same conclusions as you, as to the path forward here.
Yes, it's a bit more complicated than that as well. Łukasz kind of had he would sort of have worked on this for like 60 years with kind of not necessarily any certainty of like the finish line, out of just pure like excitement for the work and the invention and the building of something, beautiful like this. But for me, I needed something that could be done like, really fast, or like, that could, I was not going to wait decades to make a robot necessarily. So when I showed up, there was just like so many different problems that we had to like tackle all at once at the same time. And we both, like, once we started the company, left an open mind to what could change. The muscle fiber itself, like, could be developed and made a lot better. The valves could be made much better, the hydraulic power unit and so on. So we started like just tackling problems one by one once we started the company. The hand was like, would break like every few minutes or so when we started the company, and within like 18 months with just the $500,000 from angel investors, we got it to a point where you could like throw it across the room, and it'd still be okay. The biomechanical hand would still be fine. So sort of inherent to the design, it's very robust to perturbations from the environment. And the hand was also durable enough for us to bring here to the Bay Area to demo you guys and get sort of seed financing from Initialized. Yeah. Yes.
And then that's really interesting. So that sounds like a very fascinating pairing, in that he was kind of like fascinated in the end state, but just also the beauty of the intermediates of like getting muscle fibers, artificial muscle fibers, to work as an end to itself. And you layered on. Kind of reminds me of some of my previous co-founding relationships, where I was often just kind of like in it for making beautiful software, and someone else was like, often Gary Tan was often like, all right, no, let's also do something very ambitious while we're at it. I was like, that pairs very well.
Yeah. I agree.
Okay. And then like, I guess I'm curious, like, to talk through, I guess, what the hard parts are, but and it sounds like there's just a lot of them actually, which is what's interesting about this problem, which is why, like, how did you stepped into it with him already having a hand. So there on the one hand, there was kind of, the incremental goals to achieve might have been kind of obvious, but also like the scope of the entire thing is so vast. Like, on those early days, how did you think through, was it obvious what to do next, or did you actually have to like get organized and be like, all right, there's like some path dependency here? Like, how did you even approach a problem of this scope?
Yeah, so definitely within the first year, I'd say there was a decent amount of trial and error, a lot of mistake making, but at the same time, the natural next step was always very clear to me from when we started the company. So even though sometimes mistakes were made, I could trace like the calculus behind that decision to whatever information I had at that time, and today still, like, I think almost every decision makes a ton of sense for at least the motivation behind them. One example of this was deleting the proprioceptive sensing, or the sensing that gives you the joint angles inside the hand. In those first 18 months of the company, we just ditched it completely, and we built these naked musculoskeletal hands with only an actuation system and not any feedback. In other words, you can't actually closed loop control it, like knowing what the pose is at any given time step. And instead, you have to kind of write sequences where you're just telling the robot exactly what to do, with every element of the sequence. So like, go to this, move the muscle this much, move this muscle this much, and writing open loop sequences like this don't show you necessarily the controllability of the hardware. They don't allow you to feedback control it with even classical approaches, ignoring the neural network stuff. But allows you to still manually write a sequence to get you like sort of a good enough demo for us to, let's just say, raise seed financing from Initialized and get to the next step. So that was necessary at the time, especially when the hardware was already so not durable. So we had an actuation system, which actuation system here means muscles and valves, valves being the electromechanical component that's regulating the muscle length or the pressure in the muscle. So just focusing on that alone was big enough for that initial team of 12 to figure out, by just solving those problems, the biomechanics of the hand, making very durable joints, and then also making the actuation system really work. So compact hydraulic power unit, valves and muscles was sort of a big enough scope for us at that time to just produce those demos to get to the next stage, at which point we could then conquer like some of these other problems that we decided to ignore. Some of these other problems that were, in terms of building a robot, let's say critical to actually making a robot work, but sort of given the resources we had, still just sort of taking, I don't want to say taking shortcuts, but finding the fastest.
Yeah, because there's like two potential, I guess I would assume there's like two potential clusterings of like what to do next, and one is like highly functional on the components, right? Like the muscle fibers need to be durable and fire, and the other is it kind of reminds one of software systems where you architect in such a way that like there's always some unit of end-to-end functionality, which is, I think in your case, was like body parts. Like we'll start with a hand and then go to an arm, and right, which is interesting. And do you think that it sounds like, I don't know, there's so much talk. Like so from day one, you're like, all right, we have to make these more durable, but also we need to figure out the software platform and to make it integrated and in a hand shape.
We basically had no software. We had like one software engineer
Yeah.
Until last year, honestly, who was writing more or less all of the high-level control code for all of the demos that we were putting out. What we invested in when we started the company, actually, I told Lukash, like, this is almost a artificial muscle durability company. Like that's almost what the entire company needs to be to get somewhere, because there's no real producer for artificial muscles. More or less every other component, there's someone who's producing something that's durable or good enough to produce demos. Even for there may not be a producer of the valves of hydraulic valves that hit the specs that we require off the shelf for an untethered robot, but for a robot that has a cable to the grid or a tube to a central pressure source, there's plenty of valves on the market that can hit all of the requirements needed to get these robots up and running. So, but the one thing that you just can't find on the market are artificial muscles that contract as much as we want them to contract, with as much force as we want, and that are actually durable enough to put out some good demos. So that was kind of.
But it had to be both. You have this North Star that this is a durable artificial muscle company. But you're like, I realize all the incremental milestones pass through a demo.
Yes, exactly. So it's just you just have to optimize for as few problems as you can, but given the scope of the vision, that is always a large number of problems than usually a team can take on. So we have a very talented team of people. Those first 12 people on the team, basically everybody's still there. This is like a pretty generalist,
they're being
very creative team.
Poland, still in
a few of them are coming to the US office, but that was a team that got a lot done with extremely little. We had the most, I think, durable human level robotic hand in the world when we closed seed financing with you guys in May 23, and we did it on, like, I don't know, maybe let's say 1,000x less budget than your large cap Tesla or something.
And then I guess the other thing about the early decision not to have sensors is it feels like that's part of a trend that I perceive where a lot of decision points, like more like how a human works, has seemed to be like, right? Is that an accurate sensibility, or like
many decisions especially I'd say the first like 2.5 years of the company were made largely with this North Star of human anatomy pointing us in the right direction. We definitely didn't want to compromise around natural bones for a really long time before we realized before we accumulated enough musculoskeletal anatomy and biomechanics know-how to know exactly what the ramifications of making a change to a natural bone would be, like across the whole system. It's sort of like take like one gear out in like a car and like it's still going to work. Like, probably not. Like, probably there's going to be some kind of effect there.
The default is like, make it anatomically identical. And then see what you can get away with. Not
ultimately we don't have organic ligaments and organic tissue, and and skeletal muscle. So we have to still adapt around the technology that we have. But that's more or less like, yeah, it's like you're initializing an idea with human anatomy, and then if you have to make some adaptations, you do. But as much as possible, the advantage of the artificial muscle technology is that you do not have to design. Like you don't have to do nearly as much engineering design. You're just largely just referencing anatomy and copying things.
And your targets are like rooted in like
Mhm.
human muscle capacity.
Yeah.
In terms of like where you need to get to.
Yeah, like if a muscle is like in like the hand, if you have a muscle that becomes a tendon here, and then it's shaped like exactly and attached at the anatomically accurate points on the bone, as compared to a skeletal muscle, then you get like the type of flexion or extension in the case of the extensor muscle tendon that a human would. It's just a question of how much force is that muscle pulling the joints with. What is the displacement? Well, it's like how much distance is the muscle actually contracting, which will affect, for example, like the grip that the hand gets, and then speed, which is really a question of how fast the valves work. But yeah, that's kind of how we've tackled some of the problems that we have.
How should I even place the question of like what are the hard technical problems there? Is it just is it everything? Or
yeah, if you're building actuation from scratch, it's like you don't get to buy a motor that's rated for 100 million cycles off the shelf. You have to trial and error your way up to 100 million cycles, and we're, without saying exactly where we're at, we're like getting closer and closer to this. And
but
we've risen by
the V1 so it's like it's not getting it to do what you want once is easier.
Getting which part to
getting a muscle to actuate once is a much simpler problem than getting it to be like durability.
Yeah, you want like contraction and extension cycles for, let's just say, 1 to 2 years for like a consumer robot that somebody might buy, so you don't have to constantly take it to the shop. Maybe people get their cars like maintained once a year. So if you can get a year worth of durability, meaning no human interventions, that's a product that at least like I'd be satisfied with. If I were to take it to shop like multiple times a year, that'd be enough.
But from a design perspective, did it feel much lower friction to get anything at all working, or was that still like?
Oh, I mean, no. I mean, like even when we started the company, we could make a hand pretty easily. That's only going to work for a few minutes. But getting a piece of hardware that is really stable, so that you could even say train a neural network to run on the robot. You could do fine tuning on the robot, in the real world. That requires a much higher lifespan, and that's where a lot of the engineering work goes into.
In going from basically like the threat, like it's like hand to arm to torso. What were the actual?
This is one of the advantages of our design, is that rather than, like I mentioned earlier, custom designing actuation for every one of these joints, once you nail an artificial muscle fiber that really works, it's a lot of cut and paste across the rest of the body, and you're once again just attaching the muscle to the anatomically accurate points on the bones. So we were always quite confident, while working only on the hand over the first 2 years of the company, that by doing so, we would be able to take design systems of how to make artificial ligaments to construct joints, how to bundle muscles and fascia, how to interface the muscle with the bone, how to make a durable muscle to whatever desired length or contraction force that we'd require for a particular muscle group. We take all those principles and just recycle them in all the other joints in the body, and this process would go pretty quickly because the hand is the most articulated part in the body. It's very complicated there's more multi-articularity here than other joints. So you have more situations here where you have multiple muscles actuating a single joint, or multiple joints being actuated by a single muscle, and more nonlinearities with long tendons, going from like the forearm to the joints, actually puppeteering the fingers, even more so than in other joints in the body, where your muscles are kind of directly connected to the bones, not necessarily via a very long tendon. So a lot of those problems just are made so much harder on the hand. And when you get the hand working really well, you can translate a lot of those ideas to all the other joints very, very quickly. And it's how we went from working on the hand to the whole robot to conquering like full body biomechanics within a year.
Were there any surprises in moving beyond the hand, or was it like I had the
Yeah, there's still problems.
How did you like?
It's not like perfect. It's not like we got the hand.
But like you had intuitions about
yeah.
staging the problem and like what you needed to work on for the hand,
Yeah.
what you needed to work on in a broader context.
Yeah.
And like where did the staging sort of match your intuition up front, or have you been like entirely surprised? Like, oh, here's a novel thing that we didn't expect.
There are definitely situations when designing other joints where the design system didn't perfectly translate, and we had to still adapt or make some additional soft tissue components.
Kind of like in the sense of like the hand may be the most complex, but other things are still idiosyncratic in different novel ways. That
the knee joint, for example, is like is kind of strange with the sliding.
That's fascinating. Was there like has it felt pretty? I mean, it's obviously very iterative, but were there places where you're like, oh, I'm not even like, there might be a wall here?
Yeah, that's happened. But generally, those are stressful days, I guess. And, but the stress then forces Łukasz and I and the whole team really, but, Łukasz and I have had those moments where we're like hitting a wall. We're kind of like, oh, what can we actually do next? And the stress of like needing an answer usually pushes us to find some direction to break down that wall like within like a week or so, and we're trying something new and generally, and so far so good. We've gotten out of every wall we've hit.
But and like I don't know, describe that practice broadly. Is it just kind of like, let's be more creative, let's think of more things?
Yeah, usually. Yeah.
Okay.
Yeah, usually there's like almost always a way out. Let's say the energy physics of our system is definitely better than, for example, Boston Dynamics Hydraulic Atlas, which this has been discontinued. But I mean, in terms of the fact that it's maybe a robot with a similar weight and still we have a hydraulic pump and fluidic actuators. It's the energy physics are similar, but I'd argue kind of better on our robot with a lot of our soft elements. So outside of that, we pretty much know that there exists a valve that will work for us. There exists a muscle fiber that should work here, and there exists like a potential compact hydraulic power unit that's a low enough draw to get us at least a few hours of battery life out of the Android, and we know we can do all that. So yeah, it's usually just going back to the drawing board and getting creative.
Most of the wall-like things are like some sort of threshold problem where like it doesn't do it well enough, or doesn't like. Not just like fundamentally, how do I make?
Yeah, it's just we have like a very high bar to clear for like all these components. So like the muscle has to be, like I said, getting human skeletal muscles, contraction ratio for force and speed. The valve has to be working at very high pressures, high flow, low power consumption, a proportional control mechanism that allows you to continuously control the muscle rather than sort of PWM impulse. Control it with like a square wave signature, sending little packets of water into the muscle rather than just continuously injecting fluid into the muscle to achieve exact partial contractions that you may want. So the valve has to do all of that and has to be durable for 100 million cycles, and the muscle has to do all of that and be durable for 100 million cycles. So these are just very, very high bars to hit, and sometimes you try an idea and the pressure is great, the flow rate is great, but it's not proportional control, and you still have to actuated with PWM impulses, or it achieves all of that, but it's just not durable because there's some fundamental element in the valve that is just inevitably going to break within like a million cycles, and you just can't clear that bar. So then you have to still go back to the drawing board.
How do you balance? I mean, the whole thing is so novel, and the core insight is around like. The off-the-shelfy approach is like misguided. So how do you balance being like not getting to the scope of like we need to create every component from scratch?
Well, if there is an off-the-shelf thing that we can get, we will get it for sure. Are
there been components where you're like, I don't know, I'm gonna have to go spend some time figuring out if this exists?
There's like I'd say like one major like a super important critical part of the robot that right now we are getting off the shelf. I mean, it's not off the shelf. There's some customization involved from the supplier, but it's something that most suppliers of that artifact can make. So we'll get it. So we'll buy it from them, and we won't make it ourselves. But if there is none, and all the like valve manufacturers, for example, tell you that it's not possible to hit these specs on the valve, then we have to make it ourselves. And that's one area that I'm particularly proud of, that we managed to make in-house when every valve manufacturer told us it wasn't really possible.
And I imagine there's places where you thought the off the shelf might have been good enough and just didn't. You kind of had to circle back.
Yeah, well, for valves specifically, also for like a year, we decided to switch to off-the-shelf valves so that we could prototype the biomechanics of the rest of the body. We could go from hand to full Android, figure out all the biomechanics of all the other joints quickly without having to worry about building a whole set of custom valves ourselves for every single robot that we produce, to start getting some movement, start checking the joints to see how everything works. So we were so that was like a decision to move to a pneumatic system, and sort of put our hydraulic system on pause and our in-house hydraulic valve development. Well, we didn't put it on pause. We just had that running in parallel, while we just used off-the-shelf valves, a central compressor for our facility, to actuate various like joint segments, like a shoulder or a hip or a neck or something, and quickly check how it's working, and then throw it out, make the next biomechanical element, check, pressurize it, and check if it's working.
Was it intuitive that like the fibers themselves would be swappable between pneumatic and hydraulic?
Yeah, it's a fluidic muscle, so gases or liquids are compatible.
But like the compression and stuff is like going to be a little different or something.
The dynamics are different, but ultimately the pressure in the muscle is what's determining its behavior. The muscles are a bit stronger.
Some amount of either material is going to increase increase the volume of the muscle, the amount you need.
Yeah, exactly. The water muscle is like a little stronger than the air muscle. The air muscle is faster to actuate with on valves. The valves like work way faster on air. But then it requires way more energy for the compressor, because you have to, it's compressible, so you have to first compress the air before it actually gets pressurized and starts displacing the muscle, and then the hydraulic pump will be way more efficient, and way more compact, and we can make it silent and so on. But then we have to make the valve a lot faster, so that was where a lot of innovation had to be done.
How do you think about, as you go, like both, you're doing a bunch of like all this R&D, but you also need to balance like manufacturability and building your own manufacturing systems?
That stuff kind of just happens it really shouldn't be like this, but at least in the first few years of the company, it sort of just happened on the fly. Like everyone has in the back of their head that, we're kind of doing things that don't scale, but we all know that like we have to build for scale too. And so there's always a sense that if there's a piece that's being designed that we know is being designed in such a way that manufacturability is sort of a pain, like everyone kind of knows this, and it's getting, it's on everyone's head that that's probably something to be improved or changed soon enough. Like for example, when we wanted to go to the Biped, like the numbers of all the pieces just started going up big time, right? You have now like hundreds of valves, like thousands of fibers, and so if the muscle bone interface is like not good, then the problem of attaching muscles to the bone like just get 10 or 100 times worse than for the situation with just the hand. So stuff like this ends up being kind of obvious, and we have to kind of plan for semi-automatic or automatic production even at very, very small scales, just because for a single unit of robot the scale is actually pretty there are a lot of pieces in the system, so we still have to like plan for manufacturing scale even at this sort of do things that don't scale.
Even the R&D part drives that as you're going from the complexity of a hand to a body. That's really interesting. Was there anything you specifically deferred?
Tactile skin, for example, something we deferred. We'll actually probably start on that a little later this year, but force feedback from the environment is something that we take for granted and is very, very useful to us. We have quite high resolution tactile skin on our hand. It's like whole hand skin, like covers the entire hand, generates very high enough resolution force maps that you can, segment objects in your pocket, without even looking. So for a human, you effectively have like a camera in your hand, generating these like depth images, and that's essentially what you would want in a tactile skin for the robot, is whole hand force feedback that allows you to capture rich force maps of the environment and objects that are being manipulated, and to pass that as like an image essentially into your higher order foundation model, foundation policy, or whatever. So there's like a whole treatment of that we want to make to use the right technology there. That also still fits all of our mechanical requirements, with all the folds, at all the joints in the skin, and that doesn't create air bubbles, and makes still like that product wise is still like a really nice full mechanical design, in addition to actually getting very accurate sensing and of course like having it durably integrated into like the superficial elements of the hand, like the fat or the skin. So that's something that we could put off, because for now position control is enough to say like get to the next stage here for the company, which would be showing off like full bimanual demos, the hand of the torso, like using tools and doing sophisticated dexterous manipulation. A lot of that can be done by just teleoperating the robot or collecting a ton of motion capture data and across a relatively diverse array of trajectories or behaviors, and that model purely in the position control paradigm without any of that force feedback will produce us kind of the demos that we want. And the neural network essentially, if you make some kind of like shortcutted tactile feedback with like fingertip sensors or something like this, it turns out that the neural network tends to just ignore that information, and the modality of vision usually is what dominates and is what's providing the richest signal to the higher order neural network, and so it just kind of ignores all the other modalities that aren't really helping so much. So in theory, like even like lesser tactile feedback that we could add into the robot now could help a little bit, but in practice it's very little yield for like another, let's say, system to integrate into the robot.
And that's interesting, because it's kind of it's like something you assume you're going to do, but perhaps like at odds with the early decision of like, let's just the early planning thing you were talking about before. Is that like, do you have a broad view that like the software is kind of incidental and upgradable? Has that been like important through the whole journey?
I think software is not, I wouldn't say it's incidental. Good algorithms will make for a better robot brain, which will let you leverage whatever data you have better and make it more.
It's not right, but like at no point is it like super tightly coupled.
No, as long as you can still scale up data at the same time. Like a year from now, we could still make a very strong robot foundation model. We need to just say be at parity with the rest of the market in terms of how much multimodal useful robot action data we've collected. So like and there are several approaches to the foundation model and how that works, like a VLA or the world model approach, or like a diffusion policy. There are various like neural architectures for how to make a foundation model that's able to generalize across diverse behaviors and work on unseen tasks. For all of those architectures, you need a lot of you may want as much multimodal data as you can get. So for us, it's really we think about decoupling the construction of robots from the collection of data. So if we don't have to make a whole fleet of robots to collect the data required for that V0 foundation model, and we can do that from motion capture, human videos, sources, the physics simulation sources that are not the result of building a fleet of robots, that's how you bootstrap a first model and use that on your first fleet of robots to then create a data flywheel.
Which again is like, one of the huge advantages of it being so precisely biomimetic.
Yeah, the anthropomorphic embodiment, especially in the hand specifically, helps a lot with this.
And then have you along the way sort of like, as you figure out how to prune where to spend time, it sounds like part of it is you kind of assumed the software would be workable if you got the hardware to work.
Yeah, more or less. this control problem had been attempted in the past by a few folks who had some of these early motor actuated or slightly differently actuated 24-DOF anthropomorphic hands.
Yeah.
So it was always a difficult control problem to even achieve poses for a hand like that. So you have 24 degrees of freedom in the joints, and then probably more actual actuators than that, and then mapping your actuation muscles or alternate pneumatic actuator or motor actuation to the joints was always difficult because there are nonlinearities at the actuator level, at the tendons, at the joints, and so even that was a very high dimensional continuous control problem that was not very tractable for a long time to get really accurate, like let's say surgical control of such an anthropomorphic hand. Today, everything is data driven, so we have this sort of existence proof in ChatGPT that you have this transformer that's able to generalize across pretty much any modality of data once tokenized. So this is an approach that many people pursuing robot foundation models today are attempting, just to make a GPT analog for robotics in the form of a VLA model. That's all usually those are always some kind of higher order foundation model controlling robot in joint space. So in our case, what we need to do to get there in parallel while doing all this work on the hardware to get the hardware to get a full biped that's untethered and so on. In parallel to that, we have to collect a ton of data in the form of motion capture and egocentric video without robots in the loop. And then in parallel to that, we need to do some minimal amount of teleoperation to sort of really error correct away the differences between the data from human motion capture and the actual, ground truth robot actions. And then in addition, and if we have that data set, we can train our own robot foundation model, and it should work just as well across that diverse data. All we need is like a good low-level joint controller that's able to map the trajectories of the joints, which is what that data set's being collected over, to the actual muscle valve actions, like the lowest level muscle valve action. So abstracting that away is kind of the key to unlocking all of that non-robot action data in the form of joint trajectories.
Wait, so so this model is like the input is like actual motion instructions.
It's like saying like go to this pose,
yeah,
basically.
and
like,
the output is
what are the joint angles of the
and the output is directly to the joint angles, or it's like a high level thing that goes into some other joint angle.
It's like it's a hierarchical control system, basically. So the lowest level you're like the driver for the valve itself, which has some feedback about the pressure in the muscle, and then a layer over that you have the joint controller that says how do you regulate the lengths of the muscles to achieve poses, and then above that you have the foundation model that controls the robot in joint space.
Yeah, and if it's grounded in human and then tuned to the Teleop, that makes it more readily upgradable as you improve the robot and just redo the Teleop.
Well, we definitely will be getting a lot of signal from motion capture or video data, first-person video data of humans, because of the anthropomorphic embodiment. You're just able to get 24-degree of freedom actions that are much more direct to translate into clone hand actions, whereas simpler morphologies are inevitably going to be losing some information there. They're sort of trying to figure out what is the behavior being performed in this video or in this MOCAP trajectory, independent of the manipulator. So you're learning some kind of invariant representation of what's happening, of the behavior that's happening, without thinking about the manipulator. And then you're trying to like generate your robot action tokens for your parallelographer or suction cup or whatever simpler morphology you may be working with. Whereas in our case, you're just taking the explicit robot actions from that video sample or MOCAP sample.
Is it hard to have to think about this relative to, are you like throwing away generations of software as you do incrementally like better functionality on the hardware side? Like how do you think about like keeping these in step?
I guess I don't fully understand the question.
Like, do you have to like, Can you start building that model before the actual Android is done?
Yeah, for sure. It's just a matter of having a lot of reliable robot action data. So the data pyramid again looks like a little bit of teleoperation. So you're getting the ground truth of what actually the robot is doing, like the actual muscle valve actions to achieve a pose on the robot. So a little bit of teleoperation, and then a large chunk of motion capture. So this is no robot in the loop, humans wearing motion capture gloves and a video on the head, a camera on the head, to get that multimodal video joint action data. And then obviously with Teleop and that together, you're now able to have error corrected away whatever inconsistencies the motion capture glove brings, because of like, sliding of the sensors and the elastic, glove part of the MOCAP rig, or whatever other errors there may be. So the Teleop ground truth data kind of is supposed to error correct a lot of that away, and then you can finally like have internet scale pure egocentric video data that again gets error corrected away because you've collected all this ground truth, closer to ground truth, MOCAP data of the joint trajectory. So even if there's occlusions in the egocentric video data where you can't see some fingers because blocked by an object or another part of the body, you can still estimate the pose with pretty reliable accuracy because you've collected all of this motion capture data.
Is it hard to build a team that's doing these two things in parallel? Like, do you need like heavy roboticists also that are good at ML, or like what is the
data collection problem feels to me like easy compared to what we're doing otherwise. This is like probably the easiest, most straightforward thing to do in this company. Yeah.
That's well understood now. Yes. Yeah. Cool. Are you guys like, what do you like, how much outside of actually building the model, like how much software are you writing internally day to day?
Me personally,
just the team.
Oh, the team. We finally started hiring more software engineers, so it's not one guy anymore. But it really was like, when I say software, I mean like the Python layer of the stack. Let's say, we've had before that a ton of embedded engineers, or several embedded engineers who were writing the majority of this low level like firmware that we need for our machines to make the actuation system, and then that for the actuators themselves. And we've tried, by the way, a lot. I'm bringing up valves again, but we tried so many valves like that. For every valve, you have to like write new firmware for it, and you're like, at some point it felt like we were just I felt like we were reinventing the wheel, but we really needed to get to a valve that could work for this untethered biped, which is what we want, which is what everyone wants. They don't want to see this thing plugged into the grid. You want this untethered thing. So we tried so many different designs. So we had to write firmware for many valves, and that was sort of a lot of the software effort, I'd say, that was made to date. But now also like on our control software team, we're making a lot of progress towards a good vision system and super reliable proprioceptive feedback from sensing around the whole body, and reconstruction of that in the simulator and so on.
Yeah. Well, because the valve stuff, it's not just right. It's like physics, right? Like when you're iterating on writing the firmware for different valves.
Yeah. I mean, it's also like the question of like, what is the actuator of the valve, or what's like the moving element of the valve that is regulating the flow. So depending on that, that's sort of the actual dependency for where you need to like write new firmware.
Yeah.
So for example, if you're using a solenoid in like 3 different types of configurations to make 3 different valve designs, but ultimately you just have a solenoid that's the PWM impulse like controllable element in the valve, then you just have one firmware for that subset of valve ideas.
Has in those contexts has the rise of like LLM based coding been useful, or is it like too bespoke and low level?
I think with firmware is actually still where it struggles. Like it's, I think from what I've heard, at least from our embedded guys, I'm not an embedded engineer myself. So firmware device drivers is still all very foreign to me, but our guys tell me more or less that it's more increasingly reliable on the high level parts like JavaScript or Python, whatever. But for firmware, we still have guys writing that code themselves.
Cool. All right. This has all been really fascinating because there's this kind of complexity everywhere. So it's interesting to sort of at least have some sort of like high level view touching on the different parts of it. What should we look forward to from Clone?
I'm personally most excited to make an untethered biped. This feels like that's been the dream since day one, and we finally have a clear path to doing that. So that's what I'm personally most excited about. If we can get this thing untethered and walking, that would be fantastic. The goal is to do that, of course, by the end of this year, but maybe that might stretch a bit to early next year. But that's probably what I'm most excited about. There's a whole.
Does it feel crazy that you're now that close to it, or is it?
Yeah, I mean, yeah. Even when we made the first version of the full body plane, even though it wasn't walking, it was still insane to see that we got that far that fast. And now,
I mean, it feels crazy from the outside. So I'm like,
yeah.
I'm curious, like what the because I feel like you had faith the entire time.
Yeah, on some level, this is more or less where I expected us to be at this point in time.
But it's still
not. Yeah, I basically expected us to be here at this point in time, but it's still crazy.
Yeah. Sweet. Awesome. Well, thanks a lot for the time. This is really interesting.
Yeah, you got it. Thank you.